Today we're going to do more about triple integrals with polar coordinates. I just realized I'm missing an r in this equation. This triple integral, which typically turns into a iterated integral with x, y, and z as the variables, can be changed into r theta z. So the z is the same. The z does not change. The x and y do change, not into r and theta respectively, because then there wouldn't be any change, but x becomes r cosine of theta, y becomes r sine of theta. So wherever you see an x in the original function, you put an r cosine x. Where you see a y, you put an r sine x, sine of theta rather, r cosine of theta, r sine of theta, and then the z does not change. But I'm missing something here. We got to multiply by r, which is the Jacobian of the change. Jacobian. So don't forget to multiply by r when we are changing from Cartesian coordinates to polar coordinates. Well, these are polar in x, y. When we include the z, then we call them cylindrical coordinates. But essentially, it is the same thing as polar. Let's view a couple of examples. So example one, we want to integrate the function. So integrate f of x, y, z equals z. As I have mentioned in a different video, the triple integrals, the functions we're going to integrate on triple integrals are going to be reasonably simple, because otherwise the integrals get extremely complicated. So this is just a projection on the z-axis. Everything gets projected into the z-axis. And the solid we will integrate, okay, over, and I'm just gonna describe the solid. It is gonna be a cylinder, unit cylinder, so that means that the radius will be 1 with a height of 2, and we're gonna center the cylinder not on the origin, so the center of the cylinder won't be on the origin, but the bottom of the cylinder, the center of the bottom will be on the origin of the three-dimensional space. There we go. So this is a cylinder of height 2. So don't confuse my 2 with my z. The height of the cylinder is 2, and it is a unit cylinder. So that means that the width of the cylinder will also be 2. This is a pretty squarish cylinder. In fact, if you see the cylinder from one side, it will look perfectly square because it is going to be 2 by 2. And we want to know the triple integral. So we want the triple integral over E. So this is going to be, this cylinder will be E of Z with respect to the volume. And we want to know what that is. Okay. Now, if we integrate with respect to Z, Z goes from 0 to 2, so that is not a problem. Z from 0 to 2 with respect to Z. But then once we finish that part, I have mentioned in a different video that what we can do is to see what's after that, we can squeeze this down or project this down to the XY plane, since we already finished the Z part. And when we do that, we're going to end up with a circle, the unit circle. So we want to integrate over the unit circle, and that is a fairly familiar way of integrating. We're going to go from negative square root of 1 minus x squared. That is the equation of the bottom of the circle, the bottom half of the circle. Not the equation, but Yeah, that is the function. That is the output of the function of the bottom. And the top will be 1 minus x squared without the negative in front. So that is the top. So we go from the bottom to the top on the y's. And then we can go from -1. Well, then we project once the y is gone, x, y. Once the y is gone, we can project all of that into the x-axis. So we go from -1 to 1. -1 to 1, the x. Um, this is not actually too bad of an integration, even as is. In example 2, we're going to handle this situation again with a different solid. But let me show you how we change this into polar coordinates, or rather cylindrical coordinates. So this is going to be those two integrals, which correspond to the circle on the xy plane, are going to be changed into 2 pi, from 0 to 2 pi on the angle theta, from 0 to 1 because we have a unit circle. And then the z will go from 0 to 2. Whoops, I meant to say dz, dr, d theta. And I just realized again, I'm missing something. So when we are doing a change of, we are really doing a change of variable, there is an extra factor that is missing, and that is r. So we should put an r in here. I'm looking to see if I have white out, so this doesn't show us there. There, that's a little neater, not as messy, r. There we go. So that r is called the Jacobian of the transformation of going from Cartesian coordinates to cylindrical coordinates. Cylindrical and polar, they're pretty much the same, except that in cylindrical we have three variables, z, and in polar we only got 2. But this z doesn't change anyhow, so. All right, the theta is not involved whatsoever in the limits of integrations, and it's not involved in the radicand. So we can, all of this can factor out. All of this is going to have a value. So we're really integrating just one from 0 to 2 pi with respect to theta, and that's going to give us 2 pi. The z, well, the r is a constant with respect to z, so we just have the z by itself, and the z, when we integrate the z, we're going to end up with z squared over 2 from 0 to 2. So z squared over 2 from 0 to 2 is going to be 2 squared over 2. Let's just write that down. 2 squared over 2 minus 0 squared over 2. So that takes care of this. The r is a constant relative to the integration with respect to z. And then the r, we're integrated from 0 to 1, the r. And with respect to r, so that's going to give us r squared over 2. Boy, that was from 0 to 1, so that's 1 squared over 2 minus 0 squared. Whoa. So we can simplify those 2's, so we end up with 4 pi. Oh, over 2. Yeah, so there's an extra 2 here. So 4 over 2 is 2, so we end up with 2 pi. And that is that integral. Boy, that was not very painful. That was pretty straightforward. 2 pi I'm just trying to think whether this makes sense as far as we're integrating. So the average is 1, but where did we get 2? I'm trying to think of this geometrically. I might have to think this a little harder to think how it would make sense. Oh, it does make sense because the volume, yeah, the volume of this cylinder is pi, which is the area of this, the area of this circle is pi. It's pi r squared, but r is 1, so it's just pi. And then the height is 2, so the volume of this cylinder is 2 pi. Even when we multiply with the z, well, the middle between 0 and 2 is 1, so we're sort of multiplying by 1. And that's how the volume and the integral, even though we're multiplying with z, gives us the same answer, the volume. So it is a sort of a coincidence. Yeah, coincidentally, yeah, volume equals 2 pi as well. Yeah, but it's more of a coincidence because of the numbers that we're using. Just happened to work out that way. However, we could expect it also because everything is very symmetric on this integration, and the solid is very symmetric, and so there's no place for things to go one way or the other. Yeah, so this is a pretty straightforward example. The next example will not be as straightforward. Example 2. All right, so example 2 is about evaluating, again, a triple integral over a solid E, Z again, with respect to the volume. Let me back up a little bit here. The original formula we're using is this. Wherever you see an X, we exchange that X with our cosine of theta. Wherever you see a Y, we exchange the Y with our sine of theta. And wherever you see a Z, you just leave it alone. In this example we did, there was just a Z as the function, so we just left it alone. But mind that had there been an X or a Y, we would have to exchange those X's or Y's for that and that respectively. So the function that we are using is pretty straightforward. The reason why I did not want to involve an X here, at least not right away, is because if you go on the X's in this direction and multiply with volumes, you're going to end up with a number. If you go with the X's in the opposite direction, you're going to end up with a number that is negative. So X's here are going to give you positive numbers. X's back there are going to give you negative numbers. And because everything is so even out, it's so symmetric with respect to the y-axis, if you put an X in here, you're going to get 0. Because the distance this way is going to be positive, the distance that way is going to be negative. Even if we multiply by volumes, we're still going to end up with 0. So that's why I'm not using X by itself or Y by itself, because then we would probably end up with zeros. And it's good, but as an example, but sometimes it is good to also see answers that are not zeros. So back to example 2, the solid we will integrate over is going to be a cone, a straight cone, where this is going to be the origin. So there's the y-axis, the x-axis extending, and of course the z-axis is going to come from here. So there's our cone, 45 degree, and at the top we're going to stop the cone with a unit circle, so a circle of radius 1. Yep. And the equation of the cone, this side, the equation is z, which is our function, square root of x squared plus y squared. So that is our straight cone. There's a cone with an angle of 45 degrees relative to the plane. Yep. Do not substitute this for that z. Yeah, that z means f of x, y. So this is the function that we are integrating. Yeah, that's a common mistake some students do, equals z. That is what we're going to evaluate. This is the boundary. That z is the boundary. So watch out, that z is not equal to that z because this function is evaluated everywhere inside of the cone. It doesn't have to be right on the boundary. On the boundary, it is true that z is equal to that. But the output of the function is not equal to that every time. No, it's just, so if you have a little point there, yeah, so f of, I don't know, 0.1 comma 0.2 point, I know, let's do 0.1, 0.1, and then 0.4. I want to make sure we're inside of the cone. So if you go out this way, 0.1, 0.1, and if you go 0.4 up there, you're going to be inside of the cone, I'm almost sure. So what is the output of that? 0.4. Yet, if you do, if you evaluate the output of this z at 0.1, 0.1, z 0.1, 0.1, that's going to give us the square root of 0.02. When we square 0.1, we get 0.01. When we square the other 0.1, we get 0.01. When we add them together, we get 0.02. And I should have my little calculator handy. There it is. And the square root of 0.02 is not 0.4, is about 0.14. Yep. And so here we get 0.4. So this point is inside, and if you take the same inputs, x and y, on this function, then we get to be on the wall. So watch out for that. Sometimes we do make them equal if we are on the boundary, but if we're not on the boundary, then this z has really nothing to do with this z. Yeah. Anyway, let's write this as we're going to do this in two ways. We're going to do it straight without changing the variable into cylindrical coordinates, and then we're going to do it with cylindrical coordinates. So without cylindrical coordinates, all right, the triple integral of z over e, so this is, the inside of this is going to be e, with respect to the volume, is the triple integral. And we're going to go from, on the x's, from -1 to 1, on the y's, from negative square root of 1 minus x squared to positive 1 minus x squared. That deals with the circle. After we project this with respect to the z, and then on the z, so pretend you're inside of this cone. If you go and start floating down, you're going to bump into this wall. So the lowest z inside of the cone is going to be this, the square root of x squared plus y squared. And the upmost z we're going to encounter in this cone will be 1. We're going to integrate z with respect to z, with respect to y, and with respect to x. Why do we have this? it is the same reason as in example 1. You know, the cone, when we project the cone down on the floor, we're going to get exactly the same circle as this cylinder. The height is 2 here. The height of that is 1, but it doesn't matter. The projections are going to be on the floor are going to be the same. The shadow on the floor are going to be the same circle. And again, the reason why we have negative square root of 1 minus x squared is because that represents the bottom of the circle. The other one is the top of the circle, and we're going from the bottom to the top. We're integrating this way. And then finally, we go from -1 to 1. Okay, so let's do that. We're integrating initially with, oh, wait a minute. No, I was going to put the r, but there is no polar coordinates. So there's no r, there's no Jacobian to place here. It's just z as is. Yeah. Okay, so let's integrate. I'm going to pull a little fast one on you, as I have done before. This is going to be z squared over 2 when we integrate with respect to z. And we're going to plug in 1 and that. So again, it's z squared over 2. Let me start writing -1 to 1 because the other parts are not going to be 1 minus x squared, square root of 1 minus x squared. Those are the lower and upper limit. And again, this is going to be z squared over 2, I'm going to write that over 2 first. Z squared, and then we're going to plug in 1, so that is going to be 1 squared, minus this guy squared. Well, that's going to be x squared plus y squared, but we're subtracting, so I'm going to distribute the subtracting onto the x squared and the y squared that are going to come up from squaring this. So minus x squared minus y squared. Close the bracket with respect to y and with respect to z, no, we did z, so x. There we go. Okay. Then the 1/2 may factor all the way out. We don't have to have that. We're integrating 1 with respect to y. Well, that's going to be y, but we're going to plug in this minus that. Those are the same thing, except that this is negative already. So when we subtract a negative, we're going to actually double up because they're the same. So we're going to have the integral from -1 to 1 of twice the square root of 1 minus x squared. Let's put a big bracket here. I don't think we need this bracket anymore because, well, I'm going to use my whiteout real quick to erase it. Oh, wrong end. Anyway, 1/2. And then we have 2 times this root, because again, let me explain that. 1 with respect, integrated with respect to y, will be just y. Plug in this minus this. Well, when we subtract this, we're going to actually add it. So we're going to have this plus this without the negative. So we got 2 of the same, 2 of the same. There we go. Minus x squared is a constant, so we just keep the constant. And then we have the same thing. This is a constant. We're going to multiply with y with the antiderivative, this minus that. So that's going to give us 2 times the square root of 1 minus x squared. Minus, okay, now we got to be careful because this one is going to be completely different. We're going to have y cubed over 3. And this is an even function with respect to y. This is even function. So really, an even function, as you know, when you have the integral of an even function from a negative of a value to the positive of the same value, is the same thing as going from 0 to that value and then doubling it. So I'm going to apply that rule. We're going to double, and then we're going to go from 0 to the root. And we're going to end up with y cubed over 3, but we're going to plug in the root. So we're going to have the root 1 minus x squared to the 3 over 3. Close the bracket, dx. Okay. Okay, I think that that is good. So y cubed over 3. And the reason why I don't have minus this, well, you can have minus this entire quantity cubed over 3. So when we cube this, we're going to end up with a negative still because we had 3 negatives, plus the minus of the subtraction makes it 4 negatives. So now we are adding this quantity without the negative cubed over 3, and that's why we have 2 of those. Oh, so the theme of 2 applies to all the 3 terms, so we can just simplify the 2, or we can factor the 2. Yep. All right. So that was, I pulled a fast one 3 times on you, but if you're seeing this video, you're pretty good at calculus 1 and 2, so integrating that should not be too much of an issue by hand. Now, this is the top of the circle. This top of the circle. Only the top. And we are integrating it from -1 to 1, from -1 to 1. So if you integrate the top of the circle from -1 to 1, you're getting half of the circle. And the area of the circle, there it is pi. So we are getting pi over 2. If you use geometry, as long as the setup is correct, explain why you're using the geometry, but it should be okay. So the 2's already simplify. This part is going to be pi over 2 by itself. Pi over 2. All right. Now this one, don't do the same thing because this x squared affects the value of the integral. And we cannot factor x squared from an integral where x is the variable. That would be a huge mistake, a gigantic mistake. It's because it is a conceptual mistake. So don't do that. Don't apply the same logic as, you got half of a circle. Yeah, this by itself is half of the circle, but then we're multiplying by x squared. So that changes the shape of the graph. It's not a half a circle. When we multiply by x squared, we don't get half a circle. We get something, well, if x is 0, we're going to, by the way, since this is squared, we're going to get we have an even function. All the x's are squared with, so we have an even function. And so we could just integrate from 0 to 1, but we don't have the circle anymore. This changes the shape of the circle. If I have to guess, we're going to end up with some kind of bump and another bump. So 2 bumps. Yeah, we're going to have 2 bumps in there. But we're going to take this to the side and integrate this by itself. So we're going to do some side work, which you should show and as you turn in work. And we're going to integrate from -1 to 1 x squared square root of 1 minus x squared dx. So we're just going to take the integral of this part, figure it out on the side before we continue. We're going to subtract that quantity, whatever it is. So we're going to do that on the side. This is an even function, and so is this. Multiplying 2 even functions give us an even function, so we can double up and integrate from 0 to 1. Same thing, x squared square root of 1 minus x squared dx. We're going to set a substitution. So we're going to set x to be the sine of theta. And theta is going to go from 0 to pi over 2. So that is a nice transformation. And dx, the x will be, of course, cosine of theta, d theta. So we put typically this in a bracket, and we continue the equation. So we have 2 integral from 0 to pi over 2. That is going to be sine squared of theta. 1 minus sine squared is cosine squared, square root of that. Technically speaking, that would be the absolute value of sine squared. But all the numbers that are involved between 0 and 1 are positive. So we know we're going to end up with a positive number. So 1 minus cosine squared is going to be positive. Now that I think about it, 1 minus sine squared rather is going to be positive. And so the square root is still going to be a positive number. No, I think I misspoke. Only when we have a quantity squared in the radical and then we take the square root of it, then we have the absolute value. Here we just have a straight cosine. Anyway, cosine of theta for this part, and then dx is another cosine of theta, d theta. So we have 2 times integral from 0 to pi over 2 sine squared theta cosine squared theta d theta. So sine times cosine is almost sine of 2 theta. Sine of theta times cosine of theta alone is almost sine of 2 theta. We have to divide by 2. So note that sine of 2 theta is equal to times sine of theta cosine theta. So this is just a side note of the side work. So if you have sine and cosine, you can divide by 2 both sides of this equation, and you end up with sine of 2 theta over 2. So this is equal to 2. Okay, so we got sine of 2 theta, but we have 2 of each, 2 factors of each, so squared over 4, because again, we have 2 factors of each, so we actually end up with sine of 2 theta twice, d theta. The 2 and the 4 simplified down to a half, and then we have a trigonometric identity that says this is equal to 1 minus the cosine of twice the angle, so that's going to be 4 times theta over 2. Good. And then we can integrate the 1/2 by itself, and we can integrate the cosine of 4 theta by itself. The 1/2 is a constant, pops out, so we end up with a quarter, the 1/2 times the 1/2 here. And this is pi over 2, all right? And then we're integrating just 1. So integrating 1 with respect to theta from 0 to pi over 2 is just pi over 2. So that's going to give us pi over 8. Minus, okay, cosine of 4 theta is from 0 to pi over 2. This is the graph. Let me double check. That's easy to double check. So the 4 in the input of the cosine means that we're going to increase the frequency from one wave per 2 pi to 4 waves. So we're going to have 1, 2, 3, 4 by the time we get to 2 pi. So here in the middle, we got pi. Oh, I lied. Pi over 2 is going to be a whole cycle by the time we get, good thing with the double check. So by the time we get to pi over 2, we have a whole cycle of cosine. Again, this is just a side note. And if we integrate a whole cycle of this cosine, even though it has been shrunk, we're going to end up with 0, because this area plus this area is equal to this area plus this area. And the integral over those two is going to be positive. The integral over those two is going to be negative. So we end up with 0. So that integral is pi over 8. Back to the development of example 2. Remember, we paused. We didn't pause. We took this to the side, worked on it, and we end up with pi over 8 minus. Now we're going to do this on the side, more side work. Okay. I got to keep track of my pages. So that's 2, page 3. All right. So page 4. So we're going to say more side work. So we want to find the integral from -1 to 1 of, let's bring this guy back. Let's not consider the 3. we're just going to integrate this. That's side work. So I'm just going to take this guy, square root of 1 minus x squared, quantity cubed dx by itself, and see what it is. By the way, this is an even function because we're squaring the x. So whatever happens here with a positive x will happen again with a negative. So this is totally even. Even if we cube, this number is going to be already positive. So when we cube it, we're still going to end up with a positive number. So this is going to be twice the integral from 0 to 1 of the same thing, square root of 1 minus x squared cubed dx. And we're going to do the same exact substitution as we did with the previous integral. So here's the substitution. We're going to set x to be sine of theta. Dx will be cosine of theta d theta. So this is twice the integral. We're going to go from 0 to pi over 2. And then sine squared, 1 minus sine squared is cosine squared. Root of that is cosine. But then we're going to cube it. Cosine cubed theta. And then dx is cosine of theta d theta. So we're really integrating from 0 rather to 1, cosine to the 4 of theta d theta. All right, to 0 pi over 2, cosine squared theta. So I'm going to break this up into cosine squared times cosine squared. There's the one cosine squared. The other cosine squared, I'm going to replace it with 1 minus sine squared theta d theta. And then we're going to split that into two integrals, 0 to pi over 2. When we distribute this, we end up with cosine squared theta d theta minus, remember the 2 is involved in the whole thing, so the 2 distributes. Cosine squared theta sine squared theta d theta from 0 to pi over 2. Okay, here we're going to use our trigonometric identity, 1 plus cosine of 2 theta over 2 d theta minus. Now, this integral was found in the previous side work of the same problem. There it is, 2 times sine squared cosine squared, 2 times sine squared cosine squared from 0 to pi over 2, from 0 to pi over 2. And I have that this, including with the 2, after doing all this work, is pi over 8. So there's no need to redo it because we already did this. So this is going to be minus pi over 8. Okay. This 2 simplifies with that 2. Cosine of 2 theta. Well, let's split this into two integrals. The integral of 1, because the 2's are already gone, from 0 to pi over 2. Well, that is going to be just pi over 2. So that came from the 1. Cosine of 2 theta. Well, we have established that cosine of 4 theta is a whole cycle from 0 to pi over 2. So cosine of 2 theta is going to be half the cycle. This is going to be stretched. So cosine of 2 theta is half a cycle. By the time we get to pi over 2, yes, pi over 2. Because then we get to pi, a full cycle in pi, which makes sense because we are supposed to get 2 full cycles by the time we get to 2 pi. So this is the accurate picture for cosine of 2 theta if we assume this is the y-axis? Well, the integral from 0 to pi over 2 is going to be, again, 0 because one portion is above the x-axis, the other portion is below the theta axis. I meant to say theta in both cases. And so they're going to neutralize down to 0. Okay, so plus 0, that came from this cosine, but then we got to subtract pi over 8. So we end up with 3 pi over 8. Okay, so that is, this integral is equal to 3 pi over 8. That's part of our side work. So we go back to the page where I was still working on the original integral, for example, 2 minus, okay. Now, remember, we integrated this. We did not include the 3. So the 3 still remains when we transfer here, 1/3. And then the integral of that is 3 pi over 8. So the 3's do simplify. And we end up subtracting pi over 2 minus pi over 8 minus pi over 8 because the 3's simplify. And that's going to give us 4 pi over 8 minus 1 is 3, minus 1 is 2, 2 pi over 8, which is pi over 4. Okay, so the integral of this is pi over 4, or 1/4 of pi. Yeah, so if you include the height of each point, by the way, the volume of this is pi over 3. So that goes, pi over 3 is the volume of this, so that this gets knocked down by a little bit, which makes sense because it's not going to knock down, it's not going to be go down by a lot because most of the points are going to be close to 1, under 1, but close to 1. So that's why the pi over 3, so the volume equals pi over 3, goes down when we take the integral to pi over 4, because we're multiplying by the z, all the z's are less than 1, so we have to get something that is less than pi over 3, but as an answer for the integral, but it is not too far off from pi over, the answer is not too far from pi over 3 because we are, a lot of the points are on this neighborhood up here. Yeah. Okay, let's redo this example. Redo of example 2 with cylindrical coordinates. Okay. So our original integral, there's example 2, is this one. It is the integral from -1 to 1. All right, let's copy that down. The integral from -1 to 1, from negative square root of 1 minus x squared up to square root of 1 minus x squared. Integral, the bottom is the square root of x squared plus y squared up to 1 z dz dy dx. Whoa. We did this, actually. Remember? This turned out to be z squared over 2. So that's where the 1/2 comes up. And then we squared this guy, and subtracted. And then we got to this point. And then we had to take 2 more pages. This one I did geometrically. This one we took a page to figure out, another page to figure that out. So those are the 2 integrals, other integrals we figure out. And then we subtracted and we got pi over 4. So we actually went through all of this. I summarized this in half a page or so, but there are 2 additional pages of side work we had to do to get to this point. So this is actually more like 2.5 or 3 pages of work. Start all over. But we're going to change now variables. We're going to use cylindrical coordinates, which is very much the same as polar coordinates. And so we're integrating still over that circle on the bottom. So we're going to integrate using polar coordinates on the x and the y. And so this is a nice polar rectangle because theta goes all the way around. So we can go from 0 all the way to 2 pi. And r goes from 0 out to 1. That's it. So integral from 0 to 2 pi for theta, integral from 0 to 1 for r, integral for z, we're going to go from this root. But remember, in polar coordinates, x squared plus y squared equals r squared. X squared plus y squared is r squared, but then we take the root, so we will have just r. The 1 is the same. The z does not change under polar coordinates. Had we had an x instead, then you would have to change this into if it was an x, we would have to change that into r cosine of theta. If that was a y, r sine of theta. As the original formula says, exchange x's with that, y's with that. Z's, don't change them, leave them alone. But don't forget your Jacobian. So don't forget the Jacobian. So there's an extra r that pops up from changing the variables. So this is the Jacobian. And we're going to integrate with respect to z, with respect to r, and with respect to theta. Okay. So one thing to observe is, do we have any theta whatsoever? I'm going to use this. In this parenthesis, do we have any theta whatsoever, either as limits of integration or as part of that? And the answer is no. There's no theta, no theta, no theta. That's a 0. There's z and r, no theta. So all of that is a constant relative to theta. So we can just factor it out. We're really integrating the number 1 from 0 to 2 pi with respect to theta. So that's going to give us just 2 pi. That comes from this integral. Okay, now let's do that again. From 0 to 1, we're integrating the r. There is an r, so we got to be careful. But the r can factor out because the r is not part of the, let's just do this part, I guess. That's probably going to be safer. If you are in doubt, you can always just go through the motion. So this is going to be z squared over 2. We're going to plug in 1 and r. No, actually, we cannot. Yeah, we can factor out the r, but let's just do it this way. So again, integrating with respect to z is going to give us z squared over 2. Plug in 1, plug in r for z, and subtract. So we're going to have the integral from 0 to 1, r. So this is the r. I'm just copying it down. This turns into z squared over 2 from r to 1. So we're going to do 1 squared minus r squared dr. And of course, I'm missing over 2. Yep. Simplify the 2 2's. So we have pi, integral from 0 to 1 of, and distribute, r minus r cubed. Boy. And then we can say this is pi. So this is going to be r squared over 2, r to the 4 over 4. But we're just going to plug in 0 and 1. So I might just as well do that in one shot. So again, this is r squared over 2, r to the 4 over 4. We're going to plug in 1 because when we plug in 0, we're going to end up with 0 and 0 after using the fundamental theorem of calculus. So we end up with a half minus a fourth. And everybody knows that a half minus a fourth is a quarter. And then we just multiply by pi. See how much work it took? It took only from, well, this was the original, well, the setup of the original integral, setting it up using polar coordinates. And this work way beats the 2 extra pages we had to do when we did example 1 without changing into cylindrical coordinates. 2 pages we are saving. Let me double check. Yes, here it is originally. Example 2. We did it. Remember, we paused here. Well, we didn't pause. We did this integral and that integral on 2 extra pages to get pi over 8 and 3 pi over 8. The 3's cancel. Pi over 2 minus pi over 8 minus pi over 8 after the 3's cancel gives us pi over 4, which is exactly the same answer we get by doing this the other way. It is advisable to perform integrals, evaluate integrals in more than one way. At least get it started. There's a shortcut, but it's a good idea to start working both ways. So for 2 reasons, to practice both ways anyhow, and to also appreciate when we use polar coordinates in this case, or cylindrical coordinates, because they do save us a lot of time. That doesn't mean that we use them all the time. That's the thing with math. Math, a lot of people think it is very deterministic. You just gotta find the formula, or whatever works. But many times we don't know what is gonna work better. So it is not as deterministic as a lot of people think. There's a lot of thinking to do when we are working with mathematics. So those are the 2 examples. There were sort of 3 examples, but 2 examples in which we did use cylindrical coordinates. All right, with this, we stop this video.